now, sorry, at point B. So we're going to focus at point B now. Okay. So just now what we did is from point B to C. Okay, so we did from B to C. So now we are going to focus at point B. Okay, at point B, let me underline all this for you. So between A to B, between B to C. Now at point B, right? What we have now is L over R is equal to square root, or is equal to 4.71 square root of Young's modulus divided by stress U. Okay, so from here, our stress allowable will be equal to stress critical divided by 1.67. So now we have all these condition now. Okay, now we have all these condition now. So we're going to apply all these condition now, okay, to solve another problem. Okay, so as I said, this is only valid, okay, for structural steel. There are rules like this also for aluminum. Okay, the equations are different. There are also rules for wood. Okay, so if you're so I'm going to call this equation number 3. Okay, so equation 1 to 3 are only valid for structural steel. Okay, do not use for aluminum or wood, which are the two most common materials around. So for aluminum or wood, you go to your textbook, you will come across a different set of equations. That's it. Okay. Okay. Let's do another example by using these functions over here from equation 1 to 3. Okay. So there's another example that I like to do. Okay. So let's look at this example now. Okay. So this is our example number 3. So given a centric load must be supported by a steel bar AB. Using allowable stress design, so you can see this term already, okay, allowable stress design. Determine the smallest dimension of D, okay, so we have to find D of the cross section that can be used when A is equal to 24 times 10 to the power 3 pound force. Okay, and I'm not going to do B, which is equal to 36. The equations are very similar. Okay, so we're going to use that the U stress is 36 times 10 to the power 3 psi, and the Young's modulus is 29 times 10 to the power 6 psi. Okay, so we're going to formulate the problem now. Okay, so now we by looking at this, okay, you see the top and the bottom, they're pinned. Okay, so it's just a single point. So the moment, the resistance moment at the top is equal to 0, resistance moment at the bottom is equal to 0. So this is pinned, and this is also pinned. As long moment is equal to 0, it is pinned. Okay, it can, yeah, it's pinned. So from here, we can write this out now. Okay, so both sides, pinned. Okay, so therefore LE is equal to L. So this is equal to 5.2 feet. And feet is no good. We have to change to inches, which is equal to 5.2 multiplied by 12. Okay, so 5.2 multiplied by 12. You're 62.4 inch. Okay. So the next thing we have to do, okay, so I'm going to copy or we're going to look at this chart. Okay, so we need to know what is our crossover point. We need to know what is our L over R when it's equal to 4.71 square root E over stress yield. Okay, so we need to determine L over R when it's equal to 4.71 divided by E over stress yield. And what you realize about this L over R, okay, so this equation over here is based on mechanical properties. Okay, we have not looked at second moment of area yet. Okay, so this is L over R based on mechanical properties. Again, this 4.71 is determined what? Experimentally. They did a lot of experiment. They put a coefficient over there. So this will be equal to 4.71. And then square root the Young's modulus is equal to 29 times 10 to the power 6 divided by U, which is 36 times 10 to the power 3. Okay, so this will be equal to 29 power 6 divided by 36 power 3. Square root the whole thing is 28. 28 times by 4.71 is equal to 133.68. Okay, now we know the value. Okay, so now we are going to determine. Okay, we are going to determine the R value. Okay, determine the R value. So we are going to determine the R value. Why we need to determine our R value? Because on the x-axis we have what? L over R. Okay, so now I'm going to address my axis. So I'm going to call this our x. I'm going to call this our y. And then using right hand rule, this is our z. Okay, so from here, so we don't have specific dimensions, we only have variables, which is d. Okay, so if I'm going to draw, this will be our x and this will be our y. Okay, so this is how it's going to look like. Okay, so this will be from here to here is our d, from here to here is our 3D. Okay, so the line I'm going to draw now, okay, the line I'm going to draw now, this axis over here is XX. Okay, so we can formulate what is our IXX. Okay, so IXX is equal to the width is D, the depth is 3D cube over 12. So this is 3 power 3 is equal to 27 over 12 d cube. And 27 over 12, you can bring it down to 9 over 4. I'll move this over. 9 over 4, or 9d cubed over 4. Okay, so that's our IZZ. So remember, the R value that we will choose, we don't know whether it's Rx or Ry. Okay, again, we have to find the lower I value. Okay, so now if I'm going to determine Iyy, right? So Iyy is 3D. So this is our YY. Okay, this is our YY. Bear with me. Okay, give me like 1 more minute. I will carry on again next on Thursday. So that is our YY. So if that's our YY, the width is equal to 3D, and the depth is equal to D cubed over 12, right? So now 3D, so is equal to 3D4 over 12. So now this is D4 over 4. So what we know is this is, we're going to select Iyy. So what does it mean? So buckling will occur this way. So this is rotation about YY. So buckling will in this direction. And if I'm going to again draw the plane like what I've done before, this plane over here is our XZ plane. Okay, so we have to focus on Iyy, then we know our radius of direction is Ry. Okay, I'm going to stop here. I'm going to continue this example again on Thursday. Thank you for your attention. I'll still stay behind. I'll stop recording now.